But my name is Roger Oakey. I'm a nobody at DSES. I just volunteer a lot down there. I would like to introduce a couple of the people that are in the room and on the Zoom meeting here. In the back, we've got Ray Uberecken, and also Rick Hambley is on the Zoom. I consider these two folks as some of our serious radio astronomers in the club. Me, I'm just kind of a beginner at radio astronomy. So if you have any specific questions, I'll probably toss them over to those two guys to answer questions. We also have Bill Miller, who joined us this evening, who listed himself as a guest of mine, but he actually happens to be the vice president of the Deep Space Exploration Society. So I think we got pretty well any question covered here that you may come up with. A little bit about me. I'm not going to read this, but I'll point out something in here that I'm kind of an infrastructure guy. I'm more than an amateur radio operator, and that's why I kind of attach myself to DSES so much. Is that, like, if I were to put in a tower at home with a 5-band Yagi and all that, I'd make a couple contacts on it, and then I would go, okay, what can I build next? So instead of building things at my house, what this allows me to do is to do a lot of work with a really cool radio telescope down in Haswell, Colorado, and I'll get into where that is. That is just a picture of me at the feet of our antenna. This is not a small antenna. This is a pretty big antenna that's down there. So this presentation was originally done by Bill Miller. He gets 98% of the credit here. I've changed it a little bit to make the presentation a little bit more angled toward the radio astronomers. Yes, I have to stop pacing here. Okay. Sorry, to the amateur radio operators. So let me talk a little bit about the Deep Space Exploration Society. It's a nonprofit. And we're kind of bipolar. We've got two major interests down at this organization. One is amateur radio. We do have a remotely operated amateur radio station at the site. The other one is radio astronomy. For example, right now we have 24/7. We are running a scan of the sky right now for neutral hydrogen emissions. And I'll cover that. What I'm going to do here, since Hans kind of published that this is about the Deep Space Exploration Society and a little bit about our Venus-Earth contact, I will be talking about that, but I'm going to drag you through a little bit of science too, just for the fun of it. So here's our telescope. So we have a 60-foot, 18-meter dish out in the middle of the eastern plains of Colorado. So here's a picture of Colorado, and you can see kind of where Haswell is. It's about a half an hour west of Eads, if any of you are interested are familiar with Eads, Colorado. So we've got absolutely nothing around us except farm fields. So it's a very RF quiet site, except for self-inflicted injury, which we are currently working on, mitigating a lot of noise that the site itself is generating. So that's kind of the iterative process that we're going through at the moment. So a quick history is that, on the bottom there is our telescope. There are two telescopes up in the Boulder area on the, what's the name of the mountain? Ray? Table Mountain. And this is actually where DSES started, was using one of the dishes here at Table Mountain. But then 9/11 came along, and all of a sudden civilians weren't allowed on the property. And so there were a couple members that were working at the Table Mountain site, whoops, a little too early, that knew about this site down in Haswell. And so we contacted the owner of this site. I'll talk a little bit more about this. But the reason that these telescopes are out there is back in the late 50s, early 60s, what didn't we have for communication? Anyone? Satellites. We didn't have satellites. So unless you're a flat earther, you were faced with a problem of communicating over the curve of the Earth. And so the Air Force started some research into tropospheric scatter. And they had a number of sites, not just at the NIST site and Haswell, that they were looking into basically transmitting into a chunk of the troposphere, which would scatter the radio waves. You would pick it up from another on another dish and then retransmit it, and you would be able to communicate over the curve of the Earth without using satellites. So, of course, this research went on, but then along came satellites, and that solved that problem. So, again, these wordy slides, I'll let you kind of read as I'm talking. So, they basically decommissioned all of these sites and auctioned them off, and most of them went for scrap metal. And a person called Paul Plishner actually bought this site with some plans to do some work at the site, but it was just so much so much work was involved that it basically sat unused for many years until we got kicked out of the NIST site. And so we contacted Paul Plishner, asked if we could let's see if we
Hey, Roger, we lost your audio there. Maybe check your microphone and feed into the Zoom.
We're going to transfer her over to a microphone while we get new batteries for the lapel mic. Oh, and I just bumped.
That's much better. Thank you.
Let's see, where were we here? Okay, so after being there for a year or two, the then president of the organization asked Mr. Plishner if we could have the site, and he gave it to us. So we actually own all of this equipment. It's not a loan. It's not something that's going to go away the next day. We actually own the acreage and the equipment that is on the site. So let's see. So we showed up at the site. Ray was one of the original ones in 2007 that started recommissioning the equipment there. And we designated the site as the Paul Plishner Radio Astronomy and Space Sciences Center. Though he passed away in 2016, we are reaping incredible benefits from the site. Hold on here while I transfer back to the old mic. Can everyone still hear me? Yeah, I can hear myself. Okay. So let me tell you a little bit about our dish. Again, this is a lot of words. You can read it, but 60-foot dish. It's 42 dB gain, which is why we use it a lot for, or not a lot, but we use it for a lot of the Earth, Moon, Earth, or Moon bounce competitions. And it doesn't move very fast. It's an azimuth and altitude mount, so it isn't like a clock drive. But then again, if you try to relate a radio telescope to a camera, it's a 1-pixel camera. I mean, we either receive a signal or we don't. We're not getting any kind of resolution from it being in one place. You have to move it, which is one of the ways when we're doing a sky scan, we just leave the telescope in one position and it scans across the sky because our Earth is turning. Can withstand a lot of wind, which is a good thing because it's very windy out there. The dish, the superstructure is, well, it's built kind of like a brick, I guess you would say, outhouse. Underneath, it's a very strong dish. You can walk around in the dish. In fact, those two pictures are Ray here in the back working on the dish. There's access up in the tower, which if I finish in enough time, I've got some pictures I can show you of a little bit more of the site. So about beginning of COVID, Bill Miller submitted a request to the, and this is where I'm going to lack, because of my lack of being able to see the notes here. The Digital Radio Communications, Bill Miller, help me out here. Digital Radio Communications?
It's the ARDC, the Amateur Radio Digital Communications Group.
Yeah, he submitted a grant request to build this building. If you see off to the right, there's a little FCC communications trailer. That was where we were operating from originally, and so he submitted a proposal and got a grant to actually build this building, which has all the comforts of home. We have a kitchen, we have a bathroom, so we can actually host various classes and demonstrations at the facility. So we have a very comfortable facility now, unlike the trailer back then. So I told you we were kind of bipolar. So let me talk a little bit about the radio astronomy we're doing down here. This is the, RC joined. RC is another member of DSES. The hydrogen line is, actually, I'm going to come back to that. I'll just say that hydrogen line, we have a scintillation experiment, which actually looks at GPS satellites that are up in the sky and sees how much their signal scintillates as it moves through the ionosphere. And the data gets sent to the University of Texas, where they actually draw this information together from all around the world. And it's a study of the ionosphere. Pulsar logging, we're actually also in the middle of doing some work with pulsars, which I'll talk about a little bit. We have the E Callisto experiment, which is it's basically looking at the radio emissions of the sun all the time. Radio Jove, Super SIDS, a lot of these are some meteor scatter work. Pretty much E Callisto on up is going on right now. Since my involvement, we really haven't done much with the latter half there. But let me talk about hydrogen line a little bit. So hydrogen atoms that are just, this is neutral hydrogen. So most of the hydrogen here on Earth is in the form of H2. It's two hydrogen atoms that are bound together in a gas. But out in space, you have free hydrogen atoms that are not bound to other atoms. And if those atoms have a little bit of energy in them, on their own, approximately once every 10 million years, the electron will flip. Now, if you're waiting on one hydrogen atom, you have to pack a lunch, because 10 million years is a long time. But if, like Carl Sagan always says, if you have billions and billions of hydrogen atoms out there, those things are flipping all the time. And every time they flip, they emit a photon. And that photon is at 14 or 1.4 approximately gigahertz. And so what we have right now is we have a detector, or we have our telescope just pointing straight up. It's scanning the sky, and we are picking up, where these hydrogen concentrations are greater and lesser. So of course, you see them in the arms of the galaxy. They're what the original stars are formed out of, these giant gaseous clouds. And if you happen to have a number of telescopes all over the Earth looking at the entire galaxy, you get an image kind of like this, where there's a very bright band of hydrogen across the disk of the galaxy. Of course, the more that you move out, the less hydrogen there is. But there are, interestingly enough, there's two real hot spots down here in the bottom right-hand picture. Anyone have a guess what those are? Those are the Magellanic Clouds. A lot of hydrogen in those things. In fact, there's a stream, you can kind of see the start of it. There's a tail of hydrogen that comes off the Magellanic Clouds and actually comes into our galaxy. So these are, you know, galaxies that are gravitationally bound, or not galaxies, but is there a term for them, Ray? Subgalaxy, yeah, but they're gravitationally bound to the Milky Way, and lots and lots of neutral hydrogen in those areas. Pulsars. So this is another thing that actually Ray and Rick are currently working on with a couple other people in the organization. And right now we're basically getting our equipment in good shape for detecting pulsars. You know, we're doing some experimentations, getting our background noise levels down and everything. So we're starting off with known pulsars. So we're kind of rediscovering the pulsars that are already known. The pulsars is a special kind of neutron star that has collapsed. It's maybe about, you know, a little bit larger to 2 times the mass of our sun. So when it collapses, it doesn't go to a black hole, but it stays in an extremely dense state where all the electrons get smashed into the protons, and all you're left is a soup of neutrons in the star. And they're a bit heavy. You know, a star larger than our star shrinks to about 12 miles across, and 1 teaspoon of neutron star weighs about 10 million pounds. So it's very, very dense material. But what happens is, have you ever seen a figure skater when they start with their hands out and they're spinning, and they bring it in and they go faster for that conservation of energy? Well, you take a huge star and you collapse it down to 12 miles, and it's booking. It's moving very, very fast, and that fast movement, along with, you know, material still falling into it, and the magnetic fields that are around it, cause it in many cases to almost become, think of it as a lighthouse beacon. It's rotating very, very quickly, and it's emitting radio waves, and we can actually see those radio waves flashing by us at different rates. Some move slower, some move faster. So this is kind of a graphic example of what a pulsar. So this thing comes around and flashes us every once in a while. So it can only really detect pulsars that are in the correct, you know, orientation that we get that RF radiation from. So we can't really hear them. The signal strength is so low that we actually have to kind of apply statistical analysis to what appears to be noise. And I have a quick example here. So you've got this kind of noise level, and if you know the period of the pulsar, and this is why it's kind of important that we're just looking at known pulsars right now. If we know the period, we can take that data and fold it just like kind of this piece of paper over each other, and the noise doesn't add, you know, any statistical significance to the level of that signal, but that pulse does. And we're able to pick that pulse out of the background noise once we folded it. And so they might listen to a pulsar for you know, minutes or hours sometimes, typically a number of hours, and then crunch it on a fairly powerful computer, like, you know, for those of you that are into computers, you know, we have a thread ripper that has, I don't know how many cores that we can fold this material, or fold that data into and pull out the pulsar. So this is kind of what we end up with. And if you have any specific questions about this, I will toss them over to Rick or Ray here. But once you've gone through the statistical analysis and folded all of this information, you can get some graphical information about, you know, just how how loud and how accurately you picked up the data from the pulsar. These pulsars are also very far away. What's the speed of light? Someone? 300,000 meters. What? Yeah. And that is through a what? Nope, let's be more precise. That is in a vacuum. Is space a vacuum? No, it's not. So that's one of the things, kind of an epiphany that I had a while ago was there's enough matter out there as sparse as it is, that what it does is it refracts and alters those signals a little bit. So they actually get spread out. So some of our pulsars have very wide, relatively very wide signals, and some of them have very tight signals. Quite as simple as you would think it is, because space is a medium. It's not a vacuum out there. Though for us to be out there, you might as well be. So after analysis, we can analyze the data, get a graphical representation of it, and you can see along the top left of each one of these graphs, you can see the spike that gets pulled out of the data that we have for the pulsar at the period that we expect. So that's how we know that we have detected that pulsar. So let's turn to amateur radio. I've talked enough about amateur or radio astronomy. Let me get a drink here. So we do a lot of amateur radio stuff down there as well. We have a large enough dish that we can do tropospheric scatter with other stations. But the thing I've been involved with the most is this EME, or moon bounce competitions. So the dish that we have is just an incredible piece of equipment for doing moon bounce. We're one of the big guns in the contests that come around for EME, and that kind of dovetails into what I'll be talking about, which is the EVE. Again, we have high frequency. We basically have a full amateur radio station down there that can be remotely operated. Yagi that you can turn remotely and everything. By the way, we don't operate the dish. We don't move the dish unless someone's there, because it is a big piece of equipment and we want to kind of monitor what's going on. But our Yagi antenna, we can move that for amateur radio use remotely as well. I'd like to point out this future up to 8.5 gigahertz reception of deep space probes. We're currently looking at trying to receive Voyager, one of the Voyager probes. So we're going to be playing around with that fairly soon. I don't think we have a feed for that frequency, do we, down there yet? 8.5 gigahertz, the Voyager? Yeah, so guess what? It's an infrastructure project, so I'm looking forward to that. It's something new to build. So this is kind of a picture of where the amateur radio station is right now. One of the things that we have on our property, I pointed out, we've got the new building, we have the old trailer that we used to operate from. Probably about 500, 600, 700 feet away from the dish itself is a bunker. It's an underground bunker. So for all of you guys out there that sport a Y chromosome growing up, didn't you want a lair? We have a lair. So yeah, it's this underground bunker, and that's where these pictures are actually taken in that underground bunker. This picture up here with all the flare on it is, you can kind of see this is the doorway that's at the far end of the bunker. That's where they operated when they were doing the research for the dish. That's where they operated from. We wanted, especially before the technology got where we could put an SDR up in the feed, we wanted as short a coax run as possible, which is why we ended up with the trailer fairly close to the dish. Again, this is the remotely operated station. And this is, so let's talk about EME. So EME, we have a setup, a name you're going to hear a few times coming up here is Alex Nerzian. I'll just say Alex. He's from Georgia, but he doesn't have a drawl. He's actually from the country of Georgia. And he's a NASA engineer that does RF designs contractually with NASA. And so we were very lucky to have him in our organization to help design this stuff, because he designed a transmitting and receiving package. It was about 300 watts. And what was it on paper? Like 10 million watts. Yeah, it's like 10 million watts radiated power, though of course it's focused. We for the contesters, we did very, very well in our EME contests. And if I'm lucky enough, and I've set this thing up, we're about to make Bill Miller's granddaughter famous here, because anyone know what the round trip time to from the Earth to the Moon and back is, approximately? About 2.5 seconds. So this is his granddaughter. Actually, let me turn this volume all the way up here. Let's function this. Let's see if we.
Hi, this is Harper Daisy of PRT. Right there.
I'll play it one more time.
Hi, this is Harper Daisy of PRT. Right there.
Off the moon, look at.
So the trick is if you want to hear your voice, you have to be short enough. Otherwise, you're talking over it. So we have an open house, and I'll mention this a little bit later, but we have an open house, and it's always scheduled at a time when the moon is up, and we'll do moon bounce. And so really encourage anyone that even has a mild interest in this place to come down and visit us during the open house and bounce your voice off the moon. And if you're lucky, you know, we may be able to do a contact as well. So EME made us start thinking about the fact that there have been professional, you know, like Arecibo has mapped the surface of Venus using their telescope. Long live Arecibo. But no amateurs had ever done a communication off Venus. So we started looking at Venus, and Venus a couple months ago was actually in a very advantageous position. We can't be too close to the sun, because then we start picking up a lot of noise from the sun. And it can't be too far away from us because of the path loss of it being further and further away. So it was actually in a pretty good position for us to try bouncing a signal off of the Venus, which, by the way, where it was, is about a 4.5 minute round trip. So we, it required very accurate timekeeping. It required a very powerful transmitter. Alex built us a transmitter that was capable of about 2 kilowatts. Of course, we had to throttle that back to 1.5 kilowatts. For the transmission, we were in the 23 centimeter band for the attempt. And let's see if I can, what do I have? Yep. And so what we decided to do was, you know, have this kind of a couple different experiments to do. You know, can we hear a carrier? You know, if you can hear a carrier, can we do CW and stuff? So we had kind of this building pyramid of things. So, you know, the ultimate goal was to have a QSO via Venus. And again, we turned to the ARDC with a grant, which allowed Alex to build this equipment. And we also contacted Stockert in Germany, who has I think it's a 20-meter dish or so, and a 25-meter dish in Dwingelo in the Netherlands. And so New Jersey, yeah, we didn't do anything with New Jersey. So the idea was we were going to try to transmit some information and having either Dwingaloo or Stockert receive it. And because the byline for this talk was about EVE, I'll get in a little bit more detail than I normally talk about EVE. Let's see. Okay. So this is the unit. Actually, this is in the picture of me at the very beginning. This is our transmit unit. I'll just try to describe this for the folks that are online. At the very, let's take a look at the top left picture. At the very top there is a transverter that steps 6 meters to 23 centimeters. Well, just below that, above the fan still, is a amp that goes to 300 watts, if I remember right. Steps the transmitter output up to 300 watts. That then and it offsets the signal by 90 degrees, and it feeds it into two 1 kilowatt amplifiers, which are the center fans, the center 4 fans, actually going down to the lower left picture. So yeah, the amp is the one I think is labeled SSPA number 1. But the 4 center fans are the 2 amplifiers. The fans on the outboard sides are the power supplies for those amplifiers. And this whole thing is hooked up via fiber optics down to our control room. Alex had a system set up. There's lots of monitoring for temperature and fan operation and all that. And then if you look at the upper right-hand picture, on the far left there is our combiner. So it takes the 90 degrees out of phase 2 signals and combines them back into an in phase, approximately up to 2 kilowatt signal. Again, we ramp that back to 1.5 kilowatts. So with all that, yeah, we get basically 21 megawatts of transmitting power focused at Venus. We'll aside here, okay, so installing it. If you come down and you like to climb, you'll probably get voluntold to help with the dish. This Alex is here in the upper left picture. A professor, what was his name? Professor from Boulder?
Dennis Akos.
Thank you, Dennis. Dennis Akos came down. He actually brought a rubidium clock. We needed an accurate time source, so he brought a rubidium clock down for us for the attempt. And then there's me and Cody, Derek, in the bottom picture. And we installed this approximately 80-pound box at the focal point of the antenna. So how do you go? I'm going to give you a little bit of background, a little bit here. So we had contacted Stockert and Dwingaloo to receive our signals. Europe is at a disadvantage from us in that in Europe they're only allowed a maximum of 400 watts in the 23 centimeter band, which is something that's probably coming to the United States here fairly soon because of conflicts with GPS control signals, not the GPS signals themselves, but the satellite control. But we can pump in 1,500 watts, and so we contacted, we were working with them cooperatively as receiving stations. Unbeknownst to us, they applied for a variance to transmit 1,000 watts, and we heard about this, I think, at the last meeting that we were together with them, that they were waiting on this variance to come through. They didn't know if it was going to come through or not. Literally, like the day before we were going to try this, they got their variance. Okay, everyone, which direction does Venus rise in? East. So who gets Venus first, Europe or us? Before Venus rose for us, they made the contact. So you know, by the time Venus was rising for us, they were already publishing their success on the web. And however, you know, so they detected their signal very much the same way that we looked at pulsars. Is they were able to detect their carrier by statistically looking at the information over a period of time. And so a QSO hasn't happened yet. So you know, we're still looking at that, a little bit wiser at this point in time. And you know, in addition to that, there was a receive failure on their end when we were supposed to start transmitting, as well as, despite testing the living daylights out of this thing, it transmitted for about 4 minutes, if memory serves, and then a fan kicked on that had a short in it, and it brought down the transmitter at that point in time. So you know, it was one of these things, you know, best laid plans, and we you know, we gave it our best shot. There's still stuff to do, so we're still looking forward to maybe, you know, creating a QSO. I mean, the beauty of it is that you can dry run this by doing a QSO with yourself. You've got, I'm sorry, you got 4.5 minutes of transmitting time, and then you can listen to yourself. So anyway, down at the bottom, I mentioned if they do pull back on the transmitting power for the 23 centimeter bands, we'll probably just go up from there. So I've talked about radio astronomy, talked about amateur radio. Another thing that the organization is very much into is STEM outreach. In fact, it's kind of cool that we're kind of this science resource out in the middle of eastern Colorado for these really, you know, these areas that normally would have very little science exposure. Anyone seen the movie October Sky? Yeah, so I kind of picture us as kind of the October Sky thing, you know, where they were, you know, introducing folks to some of this technology. By the way, if you haven't seen October Sky, it's a very, very good movie. It's about it basically is project-based learning. Instead of standing up in front of a class and say, today we're going to learn about fractions, you go, okay, let's divide up a pizza. You know, you make a practical approach to things, and people can understand it a little bit better because there's an actual application that's there in front of you, which happens to be something my father was very much into. But we always have the open house in September, October. We try to let things cool down a little bit. Moon is always up in the sky, so we can do EME. People that show up for the open house is one day, but a lot of people stay over, and it's a dark sky site. I mean, you can see, you know, La Junta and Rocky Ford and Pueblo and Colorado Springs just barely glowing on the horizon, but otherwise it's a pitch black site. So it's an excellent site for optical astronomy as well. We are always at the Pikes Peak Science Fairs. We have awards that we give out for those. We participate in a lot of the Society for Amateur Radio Astronomers. All the work we do is published on our site, dses.science. I didn't even know that science was a top-level domain until I got involved in DSES, and presentations to amateur radio and other clubs. So, and that's what I'm here for. So, DSES, you can see the optical telescopes with solar filters on them. So those are looking, you know, during the day we look at the sun, during the night, tours, and there's one of the 4-H clubs basically caters our event. You can buy a lunch down there. So if you come down for the open house, you're not going to starve. Believe me, they have some really good food there. This Los Alamos High School Science Olympiad was very interesting. It was a group that came down, and in fact, there's, you know, bottom right hand corner is Ray talking to a group of people. What was it? It was like 80 or 90% women. Just shocked me in a good way. You know, that that when we were getting involved at that quantity in this. So, and the club, like people like Bill Miller and others, have been reaching out to a lot of these communities and are making connections, and the schools are kind of taking us up on doing these presentations for the schools. Let's see. More public outreach. Top left picture is just at one of the they call them bazaars, just get together or kind of community get-togethers. We've attended some of those. There's me and Paul, who's in the center in the bottom right-hand picture. I'm on the left. Paul Sabone is now our president of DSES, and then Alex, our designer, is there on the right. Another thing that we did is actually Rick, who is online right now, his wife took a lot of pictures and wrote an excellent article for QST magazine. And if you go to the April QST magazine, this is a 30-foot dish that was going to be basically scrapped. It was out in western Colorado, and a bunch of us went out there and it disassembled the dish. Let's see, I think, nope, I thought I had a picture in here of Ray disassembling the dish, knee deep in the dish. But yeah, we went there, we took it apart. All of the parts are now sitting down at Haswell, waiting for enough money to pour a foundation and put this in. This will probably become our more or less dedicated EME dish when it's completed. The large dish will probably stay pretty much all for radio astronomy or special amateur radio projects. So DSES has actually 2 meetings a month. We've got an engineering meeting and a science meeting and on the second and fourth Monday, respectively. And this used to say that there was a day scheduled for work trips, but at this point in time, it's as needed. Like, one of the things that we need right now is a severe mowing of our property, and there are a bunch of people going down on Wednesday. They've rented a tractor and a brush hog, and they're going to go down and mow. You can join the DSES for $50 a year, and our site is ds.es.science. All I have to say is I'm a pig in manure down there. There's so much to do, and I love working on stuff, and that's how why I got really involved in this organization. But more important than that, there's a lot of really cool science going on, a lot of amateur radio stuff going on. And I really encourage that if any of you are the least bit interested, contact us. Join up if you want. At least come down for an open house and get to oogle. No one typically gets close to radio telescopes this big without someone pointing an M16 at them. So it's kind of a fun thing to do. Are there any questions? Yeah.
Are you looking at participating in the pulsar gravitational wave analysis? I've been reading a number of papers on that.
Should I toss that over to Rick? Rick Hambley, are you? Can you address that? Could you describe that again?
I didn't hear the question.
At LIGO, there's a group of physicists that are using pulsars, an array of pulsars, to set up a long baseline gravitational interferometry, gravity wave interferometry system.
Okay, I guess there's a long baseline gravity wave interferometry, very long baseline interferometry system that I guess some physicists are looking at. Do you know anything about that? And are we participating in that?
The way the question was phrased, no, I'm not familiar with that. Right now, LIGO has 2 sites in the Northwest and in the Gulf Coast. And I actually sell products to both sites commercially. And so it is an interferometry system, but that's with just lasers, not pulsars. So I'm not familiar with using pulsars for LIGO, but I'm sure that there's more out there that I'm aware of. I'm more familiar with large interferometry systems like the Event Horizon Telescope, which I also have been involved with.
Having worked as a cosmologist, there's only been about 3 papers, I think, so far published on it. But because of the absurd frequency precision of pulsars, the early experimental work is that they can use the variation in signals from the pulsars to look at what gravitational waves have done to the space-time between pulsars, and actually using that for a gravitational or a galaxy-wide baseline gravitational wave analysis.
Well, I'd sure like to read those 3 papers.
Okay, I'll see if I can find the specifics and get them to you.
Thank you.
I'm going to real quick, since I think that I've got, I can open this up. Any other questions? Well, I'm struggling with Zoom, which is always the case.
Roger, on the EVE, back to the EVE for
Yeah.
a moment. So you said you successfully transmitted for about 4.5 minutes. Were you able to, or did you analyze or attempt to hear yourself?
No, when the transmitter went down, the whole unit went down at that point in time. So we weren't able to listen to ourselves. And also they had a failure at their site. So we don't know. We don't know what happened there.
It was actually about 3 minutes, Roger, and
Was it 3 minutes in?
Yeah, we were only about 3 minutes before the failure, and they did not hear us. And at that point, we only had about a 2 to 3 hour overlap with Europe, and so it was kind of unfortunate the way all the timing worked out. But yeah, we didn't hear ourselves, and they did not hear us. But we did transmit for 3 minutes directly to Venus.
Yeah, let's see if I've got.
Maybe the Venetians heard us. We don't know.
Here we go. I don't know if these are going to work. Nope. So just real quick, I'll give you a really fast tour of the site here. So this is our entrance, and we're actually doing EME at this point in time. I call this the Swanson microwave dinner view of the radio telescope. Again, we got about 10 million watts coming out of that dish. Fortunately, I'm a little bit off center here. Jumping. As you come in, this is actually the entrance to our bunker. And it's truly completely underground. Here is our new building off to the right, and right in front of the dish, you can see the old trailer. And let me show you what our conditions used to be. This is inside the trailer. Some of you may know Kathy Wildman. I don't know. This is Kathy Wildman doing EME a number of years ago. This is where we all were during COVID. So someone would do a little sniffle and the trailer would empty out. But very, very narrow, a lot of very, very cramped, and not much room there. You get about 6 people in there, and that's about it. Versus our new control room. So this is inside the building. We have kind of the layout here is on the left is dish control. On the right is our scientific instruments, And kind of out of the picture to the right is going to be where the new ham equipment is going to be. So we all have kind of our areas to work in. And kind of dead center there is Paul Saban. He's now the president. This is the control. We actually do have the EME equipment here. This is the control area. There's a IC 705 that we use to feed the transverter. That little Pelican case there is our EME transmitter that is feeding into an awesome antenna that has one-to-one SWR here sitting on the floor, but it doesn't transmit very well. We don't really get out very much with that dummy load there, but it's a big dummy load. More pictures of the setup. This is a good shot of the feed, and this is Ray and Alex installing the feed that we're going to use for EME, and that's a good picture of the EME dish, as well as an example of the dust storms we get down there. So we had buttoned that thing up as best we could for a couple weeks before, after testing before EME. We came back and there was sand everywhere, and we had to clean it out before we started using it. And cleaned up okay. This is the night before the EVE broadcast. Like any experiment, you struggle with last minute problems, and this is me up at the feed at I don't know what hour, working on problems that we were having with the transmitter. This is one of our checklists before we did the EVE attempt of things that we still had to do and limitations. Again, we had to make sure that we had things dialed back to 1.5 kilowatts. Here's Ray. I have no idea how high above the ground he was installing. This is the E Callisto experiment where we're listening to the sun's radio waves. Oh, I remember how high he was, about 10 feet. And he's got a gin pole up there, and he's installing the EVE. This is inside of our telescope's pedestal, looking up. There's just a couple ladders that you climb up through the center of it. Again, this thing isn't going anywhere. Boy, there's a lot of steel inside of this thing. And that's looking down at the ground from the top level deck. And this is the point of the azimuth mount for the telescope. If you have it lined up correctly, there's a little hatch that you can open up. You can then climb up where the elevation bearing is, and you can see forever. Those are the two counterweights. So it's the telescope or the dish at this point in time is tipped over, and the two counterweights are there. And if you continue going up, you can climb up. This is Mike Parsons. If anyone follows Ham Solo, HAM-SOLO, he's got a channel on YouTube where he's actually published a bunch of his adventures at DSES. And whoops, this is inside the dish. And this is how one of the ways that we work on the alignment of where the focus is. There's two threaded pieces there. You just turn that, and you can make the legs longer and shorter to make sure that the focal point is at the true focal point of the antenna. And that's just it for yet another sun. It has gorgeous sunsets out there. It really, really does. So again, any questions? I just wanted to go through those really fast because that's kind of a tour of the site. Yes? Oh, it's John. No.
This has to do with the 60-foot dish that's coming.
30 foot.
30 foot.
Yep.
Dish that's coming.
Mm-hmm.
Is that going to be steerable?
Okay. The question was, is the 30-foot dish that we're getting steerable? And the answer is yes. It's an azimuth altitude mount, just like this dish is. So it's fully steerable.
This one is not exactly what you call steerable.
Oh no, it's completely steerable. Right now, we're just leaving it, you know, you might have heard me talking about us scanning the sky. So when no one's there, we can run data collection, but we can't move the dish. That's one of our safety rules, is we don't move the dish. Okay. So it just stays in one position in what we call the bird bath position. This is the bird bath position that we have it in, and it's just scanning the sky. But no, it's a full 360 azimuth, 90-degree elevation, steerable.
Yeah, full hemispherical.
What's that?
Full hemispherical, Roger.
Yep. Okay.
So, yeah.
Any other questions? Well, thank you very much for letting me address you, and I hope and I hope I've sparked interest in at least a couple of you to come down and check us out.
You have a date yet for the open house?
Bill, have you set a date for the open house?
Well, there's been some discussion about that, whether we actually have one this year or not. In past, we've kind of used the open house as a tool to gain familiarity of people in the area, generate goodwill with the local communities, work with the 4-H group and that sort of thing. But it is a lot of work and a lot of expense for us that we can't replace. And so we're still having that discussion as to whether we actually do an open house this year. If we do, it will be, I believe, September 27th.
Okay.
So stand by and we'll let you know.
All right. Oh, how long does it take to get there? I've got a great answer for that. 150 miles, 150 minutes from Colorado Springs. Yep, and if you're on the east side of the Springs, you want to go out to Pumpkin Center and turn right. And if you're like along the I-25 corridor or anywhere south in Colorado Springs, you go down to 50 and turn left. You go down to Pueblo and turn left on 50. After both of those turns, you will end up in Ordway, and that's when you just turn east again if you're coming south from Pumpkin Center, and you'll go right out through Haswell. And we're about 5 miles south of Haswell. If you've got good eyes, as you approach Haswell, you can actually see the radio telescope off to the right at the horizon. Though it's a lot easier to go with someone that can tell you where it is to pick it out. But yeah, we're about 5 miles due south of Haswell. Okay.
Thanks, Roger.
Thank you.